Thank you for joining us here for another of the Guideline Geo webinars. I can see that we've got quite a few people in the room so far, so I think we'll make a start. A little background about me. Some of you may know me, some of you won't. My name's Jimmy Adcock. I've been working with Guideline Geo for the past 5 years. I trained as a geophysicist and then worked with a near-surface geophysics company in the UK for about 13 years before I came to join Guideline as an applications engineer. And now I'm part of the team who look after the ABEM range of products, which includes the resistivity system, which kind of this presentation has been built around. So let's have a look at what we're going to be talking about today. We are going to briefly look at who Guideline Geo are. We'll do some basic theory, just 2 or 3 slides, just to make sure we're all using the same terminology, all talking about the same thing. After that, be looking at how we can give ourselves the best chance of coming back to the office with a good result from our resistivity survey, whether that be VES or ERT. So we're going to break that down into survey planning. What are the considerations that we would take before we even go into the field? We'll look at what we can do while we're in the field to improve data quality and to make sure that what we're collecting is good, so we don't have any nasty surprises when we get back to the office. And then we'll be looking at what we can do with the data in the post-processing software. So how can we filter out bad data points that we've collected, and what can we do in terms of the inversion? As I said, I'll give you a little background about Guideline Geo, just in case there's anyone out there who doesn't really know who we are or what we do. We are an instrument manufacturer. We make geophysical systems, and we make resistivity, seismic and TEM systems under the ABEM brand, and then GPR systems under the Mahler brand. The head office, research and development are all in Sweden, and we have offices all around the globe, as you can see from this map at the bottom, which are a combination of sales and technical offices. So we cover most time zones pretty well. And so now we'll just talk about resistivity. And as I said, we're going to start with just a couple of really simple slides just to make sure we're all talking about the same things. So there are 2 main ways to do a resistivity survey. You can do a VES survey or imaging ERT survey. So VES, we are using just the 4 electrodes at a time, and in a particular arrangement, those 4 electrodes will have what we call a focus position, and that focus position is the red cross on this diagram. And so that's the point in the ground that we assume is having the biggest influence on the resistivity values that we're going to be calculating. And what we can do in a VES survey is gradually move our current injectors, those are the ones labeled A and B, gradually move those further and further apart. And as we move them further apart, the focus position, that kind of area of highest sensitivity, moves deeper and deeper into the ground. And so gradually we're going to build up this one-dimensional picture of how the resistivity varies beneath the center of those 4 electrodes. So on the instrument, we would see an apparent resistivity curve. So that's depth down the side of the plot, and then apparent resistivity plotted across the bottom. And we're calling this value apparent resistivity because at the moment, all of these measurements have been taken from the surface. So if you imagine this very bottom focus point, you know, we can't magically get in there and just measure that directly. That value that we record is kind of the combined effect of the entire ground volume between A and B. You know, that current has to pass through all of these layers to get there, and then we take our voltage measurement at the center. So we call that apparent resistivity, and what we want to be able to do is get back to something close to the true resistivity of these different layers. And we do that by taking the data off the instrument and running it through some inversion software, and we'll talk about that on the next slide. So the other alternative is ERT. So here we're still using our 4 electrodes, but now we're going to be moving them through the spread. And this is a very simple example with what we would call a Venner array, where the electrodes are all equally spaced and then it just gradually moves them along the line of electrodes. And so then we can actually build up a 2D profile in this instance. And we're not fixed to having just one type of array. You know, we can use different arrays. We can mix the arrangement of electrodes within a single measurement to try and get the benefits of different types of electrode arrays. And again, that's something that we're going to talk about in a couple of slides' time. So on the instrument, we would see what we call a pseudo section, and that is depth down the side, distance along the profile shown at the bottom, and then the apparent resistivities are represented by a color scale. And again, we're still talking about apparent resistivity, so we would need to take that data off the instrument, run it through the inversion software, and hopefully get returned a model of the ground that is realistic. So I've been talking about inversion, again, just to make sure we're all talking about the same thing, understanding what we're trying to achieve. I'm going to look at a VES data set because that's kind of the simplest way to explain this. We would have our raw data. So we've got all of our focus points and they have generated an apparent resistivity curve. So apparent resistivity against depth. And then what we do is we take that raw data and we put it into the inversion software. And the inversion software generates a model of what it thinks the subsurface might look like. Then it runs a synthetic survey over that. So it repeats exactly what we did in the field, but it does it over this model. It then plots the result of that synthetic survey, and it compares that result with our field data. And if they match, well, then you're very lucky. But more realistically, it will need to change the model to try and improve the fit between the theoretical curve and the true data. And it keeps doing this over and over again until it either runs out of attempts at trying to find the right model, or we end up with a model and real data that actually fit quite closely. And at the end of that process, the software will give us what we call a residual, and the residual is an indication of how close that model data is to the raw data that we've put in to start with. And it's normally shown as a percentage, and the lower that percentage, theoretically, the better. So low percentage would mean that the model data is tracking the curve from our instrument very, very closely. Now, I say that most of the time, theoretically, lower is better. We have to bear in mind that it still needs to be a realistic model at the end of it. So when you're doing these inversions, sometimes when people are new to the method, they're tempted to run the inversion software over and over again, let it do lots and lots and lots of iterations, trying to come up with different shapes of models. And the problem with that is that if you run too long, you end up with a model that, yes, fits very, very closely to your raw data, but may not be geologically realistic. So we need to bear that in mind when we're running these inversions. As well as resistivity data, we can collect information about the chargeability of the ground at the same time. So rather than just look at the fixed voltage that sits in the ground whilst a current is flowing, we could actually kind of consider the ground to be a bit like a battery and look at how quickly it charges up and discharges. So we switch the current on to take our voltage measurement to calculate resistivity. We then switch the current off, and we would wait then and map how the voltage drops off over time. And if you have a high chargeability, if there's a big IP effect, then that voltage will tend to drop off quite slowly. And if there's no effect, then it disappears very, very quickly. And the advantages of collecting IP data as well as your resistivity data is that if you look in any textbook, you'll see a table that looks almost exactly the same as this. And it's showing the resistivity values for lots of different geological materials and different types of water. And so you've got resistivity along the top, and then these blocks represent the kind of range of resistivity values that a particular geological material might present you. And you can see that there are very large overlaps in a lot of places. And so it's something that we talk about a lot when we're doing geophysics, and that is that one single geophysical method on its own will rarely give you the precise answer. You usually need some other kind of data stream. Now, normally, the first data stream you have is your own knowledge about where you're working. So you'll know something about the geology, so you'll be able to narrow down which of these it might be. But there could still be some quite important overlaps. And actually, if you have the IP data there as a secondary data set, it will allow you to start differentiating between some of these materials. And the kind of classic one is clay and fresh water. So if people are doing resistivity measurements for water prospection, sometimes it can be problematic. You don't know whether you're looking at a lens of clay or maybe a perched aquifer. So if you had the IP data, the clay has a very, very high chargeability. It holds on to that voltage for much longer compared to the fresh water. So by using that extra information, you can improve your interpretation. So say water has always been one of the big uses of IP. Mineral prospection is kind of its main outlet. But what we see more and more now is kind of environmental studies that are using IP. So landfill mapping and pollution mapping. So getting now into the actual meat of the presentation and what we kind of want to talk about, which is how can we make sure we collect the best possible data? Well, that starts before we get into the field. That starts with the survey planning. So while we're still in the office, first thing we want to do is we want to define the problem. What is it that we're trying to map? What do we want to find out? The better we define the problem, the better the answer we're going to end up with at the end. So we would talk about the type of target that we're trying to map, the size, the depth, and whether we need something more complex than just a 1D or a 2D measurement. So in terms of type of target, the first thing you need to consider is it going to be visible to the resistivity system? So all geophysics relies very heavily upon you requiring some kind of contrast between the target you're looking at and what it's buried in. And that contrast, if it's not there, then it doesn't matter what we do with the system, it's not going to be able to see it. So we need, in this instance, a contrast in the electrical properties. So if we're satisfied that we should be able to do that, then we can look at the other parameters of the target. So if it's something big, broad, like an aquifer in a porous geological unit, then something like VES is quite a useful tool to use. It's very simple equipment. The field procedure is nice and easy, so it's quite good for doing sort of search surveys over large areas. The downside is that it's only 1D data, so we've got a single resistivity sounding, and it makes some very big assumptions then, which is that the layers that we see in our final model, it's assuming that these are horizontal, and it's assuming that they extend to the horizon in all directions without changing. In a lot of instances, that is quite a big assumption to make. So when you apply VES, you need to bear in mind that there could be this limitation on the accuracy of the final model. But it's commonly used primarily water and mineral applications, but primarily for search surveys. So you're going to a blank area trying to determine, is there water? Are there likely to be mineral deposits here? And then once you have identified that there is, some kind of secondary survey would probably take place afterwards, whether that's more geophysics or something intrusive. If we're working in more complex geology, or the targets that we're looking for are more detailed, small, then we're automatically starting to think about ERT, because we have data in 2 dimensions at least, and we have much more detail, far more data points to play with. So the advantage is that we get a much better overview. It's also very good for monitoring. You could set up an ERT system, leave it in situ just to record over time, to look at how resistivity changes over time. But the downside, of course, would be that it's more expensive, and it can be more time consuming because there's a lot of equipment to lay out compared to 4 electrodes and an instrument with the VES method. There are so many applications for resistivity. It's a very broad method. I would say in the customers that we come into contact with, water mapping, mineral prospection, and engineering are very, very common. But we do now see a lot more of these environmental application surveys coming into the fore, looking at pollution, looking at saline intrusion, things like this. So when we talk about the target, the type of target that we have can be quite important, because the characteristics of the array that we use will determine how well we can map certain types of features. And for example, the Venner and the Schlumberger, they are very well suited to finding horizontal layering, which is why traditionally they've been used with VES, and in water surveys where you've got big, broad aquifers, potentially with quite a flat top to them. They also tend to get used a lot because people are so familiar with them. The Venner and Schlumberger method have been around for a very long time. And so people like familiarity and they use them. But there are some disadvantages associated with them, in as much as they are quite slow methods when we're talking about ERT and we have hundreds, if not thousands, of data points to collect. Dipole, different again here. So rather than with the Venner and Schlumberger, where we inject current on the outside of the protocol and measure voltage in the middle, dipole, we're measuring the current on the one side of our spread, and then we're measuring the voltage to the other side. So current goes in at A and B, voltage measured at M and N, and we can then move that pair up and down. And this allows it to be much better at defining vertical structures or confined targets like small voids, fracture zones, anything that doesn't extend particularly broadly laterally. The downside of the dipole is that it doesn't have a very good signal to noise ratio. So the signals that get returned for a given current injection are much lower. And so therefore we will see a lot more variation in our data that we record. And that can be difficult for when we're looking at deeper structures, or if we're working in noisy environments such as urban areas. So a really good compromise is the multiple gradient. And again, it's one that not a lot of people use as their first choice, maybe because they're not as familiar with it as the top three, which tend to get top billing in a lot of the textbooks. But the multiple gradient is very useful because it's injecting the current on the outside, a bit like the Venner and Schlumberger, and that allows us to have a better signal to noise ratio. And then we move the voltage pair, the measurement pair, in between A and B. So sometimes it will be closer to one of the current injectors, and at that point it's looking more like a pole dipole, and it's better for the confined vertical structures. But at other times, M and M are going to be right in the middle of our spread, and then it's almost identical to a Schlumberger array. And so for that reason, it's actually also quite good at looking at the horizontal structures, and therefore gives us this kind of compromise between the dipole and the Venner / Schlumberger arrays. So multiple gradient is really good, especially if you don't know what the likely geological setting is going to be. So we've talked about kind of how big what the form of the target is, and you know, how we can detect it. We need to think about whether it's big enough to actually detect. And so we have a rule of thumb for this, and that is that the smallest feature we could detect would be half the electrode spacing laterally and 1/4 of the electrode spacing vertically. So that means if we have a 1 meter spacing between electrodes, the smallest feature we could hope to find would be 1/2 meter across by 1/4 meter deep. That rule of thumb only really applies at the surface, because as soon as we start getting deeper, the current paths are spreading out, our resolution is reducing, and trying to predict what that resolution would be is very, very tricky. It's going to depend very heavily upon the distribution of resistivity values within the ground. But if you need to try and get a handle on how the resolution decreases with depth, one thing you can try is look in your inversion software, and generally it will show you what it's building the model from. And so this is an example from Res2D. showing what the model would look like. And each of these cells, it's going to apply a resistivity value to each of those cells and then run the theoretical survey, the synthetic survey over the top of that. And the size of these cells is based on the theoretical resolution of a resistivity survey. So it's very theoretical. It's not going to be a real world representation of what you would truly expect to see beneath your feet, but at least it gives you an impression of how the resolution will deteriorate as you get deeper into the section. If you have an application where you desperately need to have high resolution at depth, then really the only option you have is to be measuring that resistivity at that depth. So most commonly that is borehole measurement. We would lower resistivity cables into the borehole, take our resistivity measurements where those thin layers or small targets are actually lying within the surrounding material. So we've thought about how big the object is, so whether we can see it. Can we see it? Is it, is it shallow enough for us to see, or is it too deep? So again, we've got a rule of thumb that we can use here before we think about how we set the instrument up. And that is that the maximum depth we can achieve is approximately 1/5 of the cable length. So if I have a spread of cables that is 100 meters long, the maximum depth I could hope for is 20 meters. Now, in reality, sometimes it's a bit more, sometimes it's a bit less. So if we look at this table and concentrate on the end column, this depth factor, that is the value that you would multiply the spread length by to get the maximum depth. So we can see that with a Venner, if I have a 100-meter long spread, multiply it by 0.16, I would end up with a maximum depth of approximately 16 meters. And whereas dipole, it's slightly better, it's 22 meters. So we can try to predict what the maximum depth is going to be, and therefore, how the layout needs to look in the field before we get there. And then I said that the other thing we'd like to think about is it sufficient just to have 2D data, or do we actually need something more than that? And so if you have a very complex geology, it may be necessary to try and map it in 3 dimensions. And there is 2 ways to achieve this. The first is called 2.5D modeling. And that's because it's sort of halfway between a 2D survey and a true 3-dimensional survey. And what we do is we collect a series of 2D profiles at ever increasing offsets. And then we take the raw data from each of those survey lines and combine them prior to the inversion. Again, we've got a little rule of thumb, which is that the distance between your individual profiles shouldn't be more than 2 to 3 times the distance between your electrodes. If it gets much more than that, then the kind of 3D effect, the benefit of doing this 3D survey starts to deteriorate and becomes less reliable. Now, the advantage of doing the measurements like this is that we have our full spread, all of our electrodes in one line. We can use our regular spreads and protocols and get the maximum possible depth. The downside is that there is some assumptions that we're making. So a 2D measurement is assuming that the resistivity doesn't change to the left or the right of the survey line, that the variation we see just extends in both directions away from the electrodes. Now that's, again, unlikely to be true, especially if you're trying to do a 3D survey. So you can get around that by doing true 3D measurements. You lay out a grid of electrodes, rows and columns of electrodes. This is looking from top down. And then we tell the instrument to survey in all directions through that grid. So east, west, north, south, diagonally. And then that's building a 3D cube of raw data to invert. And the reason why this is slightly better is that we are then accounting for the variation between the rows of electrodes by measuring in all directions. So which one would you choose? Well, most people go for the first option, the 2.5D. And the reason is that if you want to do a true 3D survey, you get through your equipment very quickly. You use your equipment very quickly. So if you have a spread of 64 electrodes, then the biggest 3D layout you can do is 8 by 8. And if we're thinking that our maximum depth of penetration is related to the maximum distance we can get between our electrodes, and there are only 8 electrodes in the rows and 8 electrodes in the columns, then our depth is severely, severely limited. So you either need to buy a lot of equipment, a lot of electrodes to have big spreads with sort of 128, 256 electrodes in it, or you default back to the 2.5D method, where you get the full depth on each of those 2D profiles, then combine and invert. And normally what you'll find is that the two models will be slightly different. Of course they will, but often the interpretation that you make is not going to be wildly different. So if you're saying, I want to know if a feature is here or approximately where it is, you could probably do that with both methods. It's just that with the 2.5D, the edges might be a bit blurred, the exact shape of a 3D body would not be as well defined. So you have to make a compromise, but often the compromise is made up for by the ease with which you can collect the data and the depth that you can achieve. So then the final one is, well, are we happy with just a single snapshot of resistivity, or would we actually prefer to see how the resistivity changes over time? So we take repeat measurements on the same site and then compare that shift in resistivity from one measurement to another. So this little animation that you can see is, I think it came from Lund University, and it was over a landfill site. And rather than plotting the absolute resistivity values, they're plotting change in resistivity. So if there's little to no change from one measurement to the next, then the cells are left transparent. If the resistivity reduces, then the cells are colored blue, and if the resistivity increases, they're colored yellows, greens, and reds. And so what this is showing is what happens after a rainfall event. So you see the rainwater lands, reduces the resistivity near surface, but then as the water percolates through, it causes reactions within the waste in the landfill site, and those reactions are causing gas to be generated, and that gas is then increasing the resistivity near the center of the pit. So we start with the low, then the reactions begin, and we start to see the resistivity increase again. So that might be something that is required. So we've defined the problem. Next thing we need to do is look at our survey area. It's never a good idea to see the survey area first time when you appear on site to take your measurements. There's a lot of factors that we would want to take into account to prepare ourselves before we actually go to site. So, you know, the geology, the setting that we're in, you know, what are we going to be up against? So this image has actually come from a customer this week. So they were measuring over sand that was on top of some concrete reinforcement at the back of a beach. And so they needed to be able to somehow get the current into that. Couldn't use traditional electrodes. What they've done here, scrape the sand away, put a bed of clay and then a flat plate electrode over the top. So by knowing what the geology, or here the man-made situation was, they could prepare before they left the site. Then you've got to talk about ground cover. Well, how easy is it going to be for us to actually take a measurement? If you're working in the commercial world, timescales are very tight. And if you turn up and suddenly find that you're having to work through a forest, or there's a lot of fencing to deal with, then that's going to be a problem for you. So always good to try and get hold of maps, or even better, aerial photos of the site. Try and plan where your survey lines are going to be put in. I mean, consider the access as well. Do you have enough space? If you need to get to 100 meters depth, then you need to be able to lay out 500 meters of cable to be able to achieve that. And that might not be possible due to just the terrain, or if you're working in an urban environment, you know, it's unlikely that you're going to have that much open space. So we need to think about these things before we leave. And access isn't just the kind of physical constraint, we also have the time constraint. You know, we may only have a very short window of opportunity to get onto a site to do a measurement. And again, this is something that impacts the commercial world perhaps more than some of the sort of research surveys. So what can we do about that? Well, we can plan to use multi-channel arrays, multi-channel arrangements of electrodes. So this was actually listed on the pros and cons of the electrode arrangements we spoke about before. I didn't really mention them other than to say that Venner and Schlumberger are a bit slow when it comes to doing ERT. And the reason is that they are single channel arrays because they are symmetrical. So here's a Venner example. We're injecting current at A and B. And with Venner, all of our electrodes need to be equally spaced. And that means that there is only one position for a given current injection where we can actually take our voltage measurement from. So even if our Terrameter has 12 measurement channels, could take 12 readings at once, if we use this array, it's only going to be one. And it's a question I sometimes see coming in on support, you know, why is this so slow? Why is it only taking one measurement? And quite often it's because they're using a Venner or a Schlumberger measurement. If we use something like a dipole-dipole or a gradient, then we can inject current in one location. We can take voltage measurements at more positions. So the example here is a dipole-dipole. Current is going in on the first two electrodes. I can then measure the potential at various locations away from that current injection. And I can take as many voltage measurements whilst that current is flowing as I have channels in the instrument and space in my spread. So here it's just taking 4 measurements, but I could be taking up to 12. And clearly that is going to give us a massive increase in efficiency, really reduce the amount of time we're surveying. But not only that, means we need fewer current injections. And if we need fewer current injections, then our power supply is going to last better, last longer through the day. So big advantages to be had with using the multi-channel arrays. Again, on time constraints, we need to think about if we've decided to use IP, how that will impact our survey. So this is what a typical IP waveform looks like. This is what the current injection looks like. We switch the current on, we wait for the voltage in the ground to stabilize, then we take our resistivity measurement. We then switch the current off so that we can take the IP measurement, the chargeability assessment. And the current needs to be off for at least as much time as the current was switched on for to allow the complete relaxation of the ground, complete dissipation of the voltage. We then put the current on in the opposite direction and take another measurement so that we can counteract any drift that might happen during the measurement cycle. Then we switch the current off again to take another IP measurement in the opposite polarity. And then we have a background measurement just to, again, help us reduce any drift that's happened between the start and the end of that measurement cycle. So all that means that one data point takes 5 seconds. 5 seconds, not very long, you say. But if you've got hundreds or thousands of data points to collect, then 5 seconds is a lot of time. It adds up, especially if the instrument needs to repeat the measurements, needs to stack the measurements. That means that we are going to be talking about a big increase in time over a traditional just pure resistivity measurement where the current is on in the positive direction and then switches directly to the negative direction and then back to positive and just keeps cycling. So how can we overcome that? Well, fortunately, the Terrameter allows us to use what we call a 100% duty cycle. It's unique in the IP world. And what it's doing is instead of that traditional waveform for the IP, we discard that and we use a more traditional resistivity method where the current is on in the positive direction, then immediately switches to negative, then immediately switches back to positive. It just keeps doing this direct switch over, positive, negative, positive, negative. And what we do is we use that, that delay time in the measurement to actually extract the IP effect, because the reason that the voltage doesn't stabilize immediately, the reason why we don't start the resistivity measurement immediately, because we're waiting for the ground to charge up. So why not use that to our advantage? So what we do is we wait for the switchover period and we map that curve. And that gives us a number of advantages. One, we're taking out the off time, so the measurement is much faster. Two, we've got a bigger effect. When instead of measuring just from positive to 0 or negative to 0, we're going all the way from positive through to negative. So it's much easier to see that chargeability effect, to see the shape of the curve, get a real idea about how the IP effect is operating in that region. Because we've shortened the time, that allows us to actually stack more often. And IP values are very, very small. The voltages we're recording are tiny. So if we can repeat the measurement many times without really extending the survey period, then that is a definite benefit in terms of getting good quality IP data. So talked about those kind of physical parameters and time, and I touched on noise when it comes to the IP measurement. Well, that's actually true for resistivity as well. I mean, anywhere where we take a geophysical measurement, we want to have as little background noise as possible and improve the ratio of the signal that we're generating to that background noise. And so again, we come back to the type of array that we're using. And if we're using a Venner, a Schlumberger, or a gradient, they are what we call a nested array, because the current path looks like a nest with the voltage pair sitting in the middle. And it's always in between A and B. So as the current is spreading out, the voltage measurement is always where the current density is highest between the two current injectors. So the example that I always use when I do training is I say it's a bit like me sitting here talking to you now. I'm inside this room. I'm the loudest thing you can hear. You might be able to hear a bit of noise outside or from the rest of my house, because like everyone else, we're working from home at the moment. You know, so you will hear some background noise, but I am the loudest thing, hopefully. If we look at a dipole measurement, however, here, then the current injectors are off to one side compared to our voltage measurement. And that means that our voltage measurement is always where the current density is gradually reducing. So the equivalent would be me standing in the corridor giving this webinar. So you'd still be able to hear me, but the volume of me talking compared to the volume of my 3-year-old son shouting for biscuits is, you know, there's not a big difference. And so then it's very difficult to discern what I'm telling you from that background noise. And so it's the same for resistivity. It's very difficult to discern the signal that we're injecting from background noise, especially in, for example, urban environments. So we've looked at our measurement parameters before we've gone into the field. We've tried to decide how to set the instrument up and how we're going to take measurements. Is there anything else we can do? Well, if you're still not sure, you can always try doing some modeling. And this is something that I do quite a lot when customers say, this is my application. Do you think resistivity will work for me? And what you can do is here using a free piece of software called Res2D Mod. It comes from the same people who make Res2D Inv, Res3D Inv. And you can try and bash out what you think the geological setting would be. So define the kind of background resistivities and then the resistivity of the targets that you're going for. And if you've got time, you can make this as complex as you like. You can then run a synthetic survey over the top and see what the pseudo section would look like, what the raw data would look like, and then run that through the inversion software. So kind of mimic what we're going to do in the field and see what the result looks like. And that will quickly tell you whether or not you're likely to be able to see the target you're interested in, how well you can define it. So it takes a bit of time to be able to set these models up and then run the inversion and, you know, try and get the model correct. But it can really be worth it in terms of deciding whether there's any point actually applying resistivity or whether you should try and think of a different method, perhaps seismic or, you know, some other geophysical tool to try and detect whatever the target might be. So we've got to the end of that. We've defined the problem, determined that survey area is suitable and how we're going to attack it and what measurement parameters we're going to use. Then we're always going to check our equipment before we go into the field. And then once we're in the field, then we need to kind of think about how can we maintain or ensure that we're collecting the best possible data. And so I've kind of narrowed it down to the three main problems that I see on the technical support that we do. So when customers send me a data set and say, this is very noisy, or I'm getting a lot of negative values, could you help me investigate why? These three topics are almost always the reason being. So first one is electrode placement. Quite simply, it's just that the ground that we're trying to put the electrodes in is not very helpful for us. So it's very stony, or it's particularly dry. The natural material has a very high resistivity. So it's difficult to persuade the current to leave the confines of the cables and electrodes and enter the ground. And if you were to actually look at what contributes to the resistance between the current injectors, we have the resistance of the ground itself, and then the resistance at each of the electrodes. And that is by far and away the largest contributory factor. That is the thing that is adding the most resistance to that path. It's the electrode contact. And as that electrode resistance, the contact resistance goes up, then what we're going to see is we're going to see the current go down. And if the current goes down, then the signals that are returned are going to be smaller, and therefore the quality of the result that we get is going to be poorer. So what can we do? Well, the first thing is to make sure we use the electrode test. Always do an electrode test. The instrument has this built in, and it will show you what the resistance is on each of the electrodes. And if you find that any of the electrodes have a particularly high contact resistance compared to the others, then you can focus on them trying to reduce the resistance. And if it's not going to be possible for whatever reason, you've tried and you can't do it, or there is an outcrop of rock that is causing the problem, you can actually look at how often that electrode is going to be used in the measurement and make a kind of qualified determination of whether removing that electrode from the measurement is going to be massively detrimental to your final result. So here you can see that this particular electrode, cable 1, electrode 6, it's going to be used 6 times to inject current. It's going to be used 15 times to take a voltage reading. So I know kind of how many data points I'm likely to lose if I was to say I don't want to use that electrode anymore. Then the two methods that we have of kind of improve the contact resistance and therefore increase the amount of current that can be injected are to reduce the resistance physically of the material that is there. So water it, add gels or saline solutions, use clay, as we saw in that plate example, as a way of increasing the footprint of the electrode, or just increase the amount of surface area that we have in contact with the ground, because more surface area gives the current more room to spread out. So we can hammer electrodes in deeper, we can try using longer and longer electrodes, or actually multiple electrodes. So take 5 or 6 electrodes, connect them all together, and then connect one back to your spread cable. And that acts as if you've got a much larger electrode in the ground. This is a big one, the power supply, the battery. And quite often it's either that the battery has not been charged overnight, and I will hold my hand up, I've done that before now. The battery doesn't have the capacity, it isn't high enough rating on it, amp hour rating, to be able to deal with the current draw from a resistivity measurement. Or it's a depleted battery, which can be a real problem. Depleted battery is one where the cells inside it have started to degrade, and when the battery is resting, the voltage looks quite good, but as soon as you try and put any kind of load upon it, it fails massively. So just as an example, if you think of a typical sealed lead acid battery, lots of people use these as their power supply. that will be made up of a series of cells. And normally a 12-volt battery has 6 cells in it, and the voltage should be 2.1 to 2.2 volts per cell. So a fully charged, healthy battery with no load on it should return something between 12.6 and maybe 13 volts. If you were to take a battery out of your storeroom and it's been in there for a little while, put just a regular multimeter on it, and it was to read 12 volts, some people might go, well, it's probably good enough to take out. It's a 12-volt battery after all. But if we look at this this diagram, it shows the state of charge of the battery in percentage against the voltage per cell. So if you've got 6 cells, 2 volts in each of them, making 12 volts that you've measured, that battery actually only has a 25% charge. It's a 25% capacity, and that's without any load on it. So, you need to kind of think, is this battery good or bad? And the problem is that if we have a poor battery, then we're going to end up with the current transmitter struggling to be able to generate high levels of current. We're going to have to use reduced power if we want to get through the day. And in the worst case scenario, if the voltage drops below a certain threshold, the transmitter will just shut down to protect itself. So what do we do? Well, these are really easy things. These are simple things, but sometimes they get forgotten. And that is, we can use a battery with a decent rating, so anything up above 55 amp hour. Problem is that the higher the amp hour rating, the bigger the battery, the harder it is to transport. Keep a good charging regime. So when you get back from the field, make sure you charge the batteries straight away, both the ones in the instrument and the external 12-volt battery, because if it's dropped down below 75%, it's going to start doing damage to the battery. And if it's left in that uncharged state, it will really kill the battery very quickly. So if you want to be using them again and again and again, good charging regime. Think about perhaps having an in-field charging solution. So we don't recommend putting a generator onto the instrument because it's very difficult to get a generator that can cope with the fast changing load that appears during a measurement cycle. Also very difficult to find one that outputs a really nice clean 12 volts. And if you don't have clean 12 volts going in, you're never going to get a clean signal coming out, and you're going to get dirty data coming back as well. So best thing to do is maybe to have 2 batteries that you can cycle. You can have one attached to the instrument. You can have the other one just attached to a very small one of these handheld generators that's just giving that a good top-up charge whilst the other battery is being used, and then you can swap them over if you need to. You need to think that when a resistivity measurement is underway, the current is changing very quickly, and that's a lot of demand to try and put on a generator. So you could always use batteries as a filter. So you have a couple of batteries attached to the instrument, and then you would have your generator attached to the far side of the batteries. But the easiest way is just to have the rotating system. Just get rid of old batteries. That's always a good one. As soon as they show any signs of depletion, send them to a recycling center, get rid of them. And then sensible transmitter settings. If you are using the highest power settings, the instrument could be drawing 30 or 40 amps out of a battery. And so a 12-volt car battery is not going to last a very long time if you do that. It's going to be dead by morning break. So try and use sensible settings, which takes me on to the next page, which is poor data based on poor choices of transmitter settings. So we want to try and pick settings that suit where we're working. If we use values that are too high, we're just going to kill the battery in a very short space of time. But if we use values that are too low, it's going to impact data quality. So how can we deal with that? Well, the easiest thing is to use a sensible start setting. And we have those preloaded onto the instruments. So these are nice middle ground settings that will work on sort of 75% of sites. And then once the measurement is started, you should be watching the data as it comes in. It's boring to look at a list of numbers, but it will guarantee that you'll go home with better quality data at the end of the day. Don't sit there watching the pseudo section. It's not interesting, and it doesn't give you a great idea of data quality. If you look at the results table, we have a standard deviation column, and that tells you how stable the voltage that we're measuring coming back from the ground is. And if that is stable, then we can be pretty certain that we're getting good results. So if this standard deviation value is below 1%, then I'd be quite happy to just let the instrument continue running, and I'll watch it to see whether they, go up above that threshold or not. And if they were, if the values kept creeping up, towards 5%, above 5%, then what I would do is I would look at what the transmitter is doing. So this row at the top is showing me the transmitter values, so current, voltage that's being used to push the current into the ground, and then how much power. And I will see if one of those is hitting the limits that I have set on the transmitter. So if, for example, I had set my transmitter to 100 milliamps and I keep seeing 100 milliamps appearing on this this row, then I would say, right, I've caused this instrument to hit the buffers and therefore limit the quality of the data. So I would go back, increase the current to a higher level, and then start the measurement again, or continue from where I was if I haven't collected too much data already, and see if I have improved the quality of the data. Now, the instrument is designed to actually take the deepest measurements first, and they're going to be the hardest ones. They'll be the smallest signals. So if those first, few current injections are good, then you can be pretty sure that the rest of the data should be good as well. In terms of kind of what we can physically do to the instrument to help with data quality, well, just always take with you something to keep the connectors clean and dry. What we're trying to avoid is getting too much moisture inside the connectors, or worst case scenario, some kind of foreign object in there that could cause, as we see here, a short between some of the pins. So worst case scenario, that could cause damage to the instrument. Best case, it's going to cause pretty poor data. So something that we can make sure these are clean. If anything gets in there, we can pick it out. There's something that's not going to leave debris behind itself. I have a little electrode contact improvement kit, which amounts to stuff to pour on the ground to improve the resistivity, or stuff to clear loose material away. So what you'll sometimes find, as in this example, is that the topsoil has a lot of air or vegetation in it. And if you look here, there was next to nothing that would conduct electricity in this topsoil. So we had to dig down about 20 centimeters to get to something that we could put an electrode in that would give us a good contact. So make sure you've got something that will help you clear away that topsoil. In terms of what we can do in terms of keeping the instrument healthy in a long term, well, make sure that the batteries are always charged, as we said, when we come back to the office. And also, if it's been wet during survey, the instrument is IP66 rated. So that means it's completely dustproof and it will withstand high pressure water jets. So heavy rain is not a problem for it, but there will always be moisture in the air, and that moisture can get onto the connectors. So when you get back, especially if you've followed this particularly bad example of survey practice, make sure that you put it into your nice dry storeroom and leave the caps off for a couple of days, just to make sure that any moisture that has got in there has plenty of opportunity to dry back out again. And I am always duty bound to say that it is never a good idea to operate in rainstorms. So we laud the fact that our instruments are IP66, very field rugged instruments, but the problem with operating in thunderstorms is you don't even need to be directly beneath the thunderstorm to get very, very large voltages induced in your cables, because effectively they are acting as a massive antenna, and in the air you have a lot of electromagnetic energy that can induce these big voltages. And they're not just dangerous to the user, but they can quite easily exceed the regular voltage protection that you might have on an instrument. Other ways that we can check the data quality whilst we're in the field, we can take what we call reciprocal measurements. So that is taking our layout of electrodes, current and potential measurement probes, and swapping their positions. And we should get the same resistivity back. If we don't, it tells us something about the fact that our assumptions, our 1D or our 2D assumptions, are not fitting on this particular site. This is very easy if you're doing a VES survey, because you can just unplug the connectors on the end of the instrument, plug them back in, repeat the measurement. If you're doing ERT, then you would normally write a second protocol, and it doesn't need to be a complete protocol. It can just be a sample of data points around the profile to act as a comparison. And we can actually then give some kind of quantitative estimate of how closely our model is or our survey area is fitting with the assumptions that we make in the model. Cross lines, again, these are very useful and help us to define whether our assumptions are correct. And so here you can see an ERT model where we've put a cross line in, and where the cross lines meet, what you should see is a good tie-up between the resistivity values if the model assumptions are working sufficiently in that region. If there's a big change in either the kind of depth to a particular layer or the absolute resistivity value, then that tells you that something is happening off the line of electrodes that is impacting the resistivity values. And then, as we discussed before, the really easy one is just to keep an eye on these standard deviation values. Okay, because of my problems at the start, we're going to overrun slightly, so I apologize. It's about another 10 minutes. So the presentation itself takes about an hour. So we're going to have 10 more minutes, and this is just looking at what we can do with data when we get back to the office. And we're going to look at the companion software that comes with the Terrameter LS to start with for the initial phase of processing. And then for the inversion, I'm going to quickly look at Res2D. And I've chosen this one because we kind of aimed this webinar at basic to intermediate people. And Res2D is a very easy software to get into in terms of how it operates and the kind of guidance it gives you when you load data into it. The other software package that we market is AGS Workbench, and that is an excellent tool. It has some real great advanced functionality, but in terms of a kind of short webinar, it doesn't really lend itself to that. So I think we'll probably do a webinar on the Workbench later in the year. So keep an eye out for that if you're interested. And also, I'm about to end the kind of PowerPoint slide. So I thought I'd just quickly say that if you've been interested by some of the stuff you've seen here, we've gone through it very quickly. We're actually going to be presenting some workshops at GSA, Geological Society of America 2020. Because of COVID, it's gone completely online, and they've changed the format slightly. So you can actually just sign up for the short courses. You don't need to sign up to the whole event. So if you're interested in this, we'll be doing getting the best and making the most from ERT. We'll be looking at all of this in much more detail. And as I say, there's just a small fee associated with that. And you can get a full 4-hour workshop on what we've done. Right, so let me swap to the software. And as I say, we're going to start with Terrameter LS. And this is the companion software that we would download data into from the instrument. So what I'm going to do is I'm actually just going to load in a project that I've worked on previously. So this is kind of the database that would have come off the instrument itself. So what we can do when we have a data set from the instrument is we can, first of all, just look at the summary. So I appreciate that in the commercial world, you might be dealing with the data, but weren't necessarily the person who was out on site. So if you look at the summary for a particular measurement, it'll allow you to see the settings that were used during the measurement, and you can make sure that nothing has been set up incorrectly before you start. I can also have a quick look at the log from the measurement, so I can see whether they had problems with, error messages, bad data, they struggled with getting the system to pass the electrode test. And on that topic, I can also look at the results of that contact test. So we can see here that the contact resistances on each of the electrodes were relatively high. So I know that there may be a problem in some places. I may have some poor quality data just because it was difficult for them to get the contact resistances down. If I was to go back to the summary and just take a click on one of the stations, so this is one of the instrument positions, it will show me on a map where the instrument was during that particular measurement period. And if I look at the aerial photos, then I can see, right, okay, so they were working on some kind of, it looks like gravel track, so it's not surprising that the contact resistances were a bit higher. So we can get that because the instrument has a GPS built into the handle, and it will log a GPS location with everything that it does. If I want to have a quick look at the real data and start with the filtering, then I open the database up proper, where it will show me all of the data values collected during the measurement. Now, I warn you, when this comes on screen, there's a lot of information to look at, but there's only a few columns that we really need to concentrate on when we're doing the filtering. So it's telling us the measurement ID. So I've just sorted that from smallest to largest. So we can see measurement ID number 1. That was the first current injection. And it will tell me which of the measurement channels the data was collected on, which electrodes were being used, the current that was injected, the voltage being used to push that current into the ground, and then the signal that we get back on each measurement channel. So from each receiver pair. Then calculates the resistance, and based on which electrode array we've used, we can then calculate our apparent resistivity. Towards the end, we've got information on the IP windows as well. And then right at the end, we can see what the external battery voltage was. So you can see this one was at almost 12.6. That's good quality, healthy, fully charged lead acid battery. Happy with that. So I wouldn't expect any of my problems to be coming from the power source. So how would I go about filtering? Well, the first thing I'm going to do is I'm going to sort the variability column. So that's our standard deviation. And I'm going to be really mean on this data set. I'm going to get rid of anything above 1% standard deviation. And what you would do is you would kind of balance how many data points you want to take out. So you want to you want a good data set, you want a good spread of data points right the way through your profile, but at the same time, you don't want to take anything that's really bad. So you would kind of base your threshold on the site that you're working on. If it was a noisy site, then you might set your threshold a little bit higher so that you can maintain a few more data points. But here, I'm going to cut it out at 1%. So I just right click and say filter, and they're all gone. And I can see down at the bottom that I've taken out 37 of 2,794 data points. So that's not too bad. The next thing that I would then do is I would look at the input voltage. So this is the strength of the signal coming back. And as a rule of thumb, we would generally say ignore anything below 1.5 millivolts. So 1.5 millivolts is 0.0015 volts. And here our smallest measurement is 0.0032. So we're more than double that threshold. So I don't actually need to filter anything out here. But if we do have those very small values, the assumption is that they're probably falling into the background noise. If we want to be sure, what we can do is we can actually look at the full waveform of these measurements. So whereas that table is the averaged value for current injected and voltage coming back, this is sampling up to 9,000 times a second how the injected current and voltage changes and how the signal coming back out of the ground changes throughout the measurement cycle. So if I look at what the instrument injects into the ground, in black is the current cycle. So you can see it's a nice, even, sinusoidal type current injection. And then the brownish color is the voltage varying to keep our current constant. If I look at the received signals, then each one of these colored lines is a separate measurement channel. It's left my current in there for reference, and then I can see what each measurement channel did. And what we can do is we can zoom in to one of these just by dragging and clicking, and we can see how much noise there is in the background. So we can then make an estimate of what would be a sensible cutoff for that millivolt value. So this is really useful if you've got some weird effects in the data and you've cancelled, you've said, well, I've checked the electrodes, I know it's not those, I know it's not the battery, I know it's not the settings. You can come in here and see, is there something else that could be causing that problem? So that's basically it. I've filtered my data based on how much the data had varied, filtered it on the strength of the input signal. I can have a quick look on the apparent resistivity, so make it small to large, make sure there's no obvious statistical outliers, then make it large to small, and it varies pretty smoothly into these values. So I don't really need to filter anything else out, so I just right click and export. I'm going to export it to the Res2D format. I'm going to export it as a flat data set, but I could apply topographic correction if I want. Save that. And then I'm going to switch to Res2D and just look at what additional functions we have in there before I wrap it up for today. So in Res2D, I can read in my data file. Here we go. So open that up. And the reason why I like Res2D, for people who are new to resistivity method, especially if they're new to even geophysics, is that it is a very takes you by the hand. So I've read this data set in, it's given me the header information about this data, and it's immediately given me a message. And what it says is that the resistivity values vary very rapidly in the top layers of my data. And it says that I would actually get a better result if I allow the system to use a more refined model. So when we looked at that diagram of cells that the software uses to build the model with, this is saying, well, do you know what? If you put more cells across the model, then that allows me to vary the resistivity in the model more smoothly, and I can probably cope better with this fast changing data set that you've loaded. So it tells you where to look in the manual to do this. So from experience, I know that I just go to my inversion menu, model discretization, discretization, still not sure it's a word, use model refinement, and then use model cells with widths of half the electrode spacing. So making a smoother model. So I say, okay, it asks me to read the data in again. I do that. And now we can do a bit of filtering. So the first step would be to say, exterminate bad data points. So I can come in here, and this is showing me, rather than like a true pseudo section, this is grouping data values that share similar electrode arrangements. So it's putting them all next to each other on their particular, either depth or the electrode pairing. And so what should happen here is the resistivity values represented here are not absolute, it's relative from one data point to the next. And so you wouldn't expect to see a big jump in resistivity. And if we did, then that would suggest that it's a spike, that it's a poor data value, and we could therefore try and remove it from this data set. Now, if you've done your filtering in LS Toolbox, there isn't really much to do in here. You should have got rid of most of those. If I just move this up a bit. The best I can say is, well, maybe there's a spike here, but if it's bad data, you'll really see these big jumps. And so you can just click on individual data points and remove them from the data set before you start the inversion. So when you say exit, it asks you if you want to save the edits. I'm going to say no, because it's quite clean to start with. And then you can run the inversion. And again, as a beginner, there are really two options when you start doing the inversion, either a robust method or a smooth inversion. And smooth inversion doesn't allow the resistivity to change very much between layers or within the model, and it doesn't allow the resistivity to change rapidly from one cell to its neighbor. So with that smooth version, it's best suited to where geology changes relatively smoothly. So weathered top of your bedrock into gradually more competent bedrock, or a relatively organic soil where the water content might increase slowly. If you've got somewhere where, say, you've got a sandy layer over a very solid bedrock, a very sharply defined feature, or you're looking to define voids in limestone, something like that, then you would expect there to be a massive resistivity contrast between your target and the material around it. And so then you could use this robust method. So inversion methods and settings, select robust method, and that allows the model to have these bigger jumps in values. If I was to display a data set that I've already inverted, so I'll open one up. Let's go for this one. So the inversion has been run on this. I display my data. We can see in here that we have our raw pseudo section. That's what came off the instrument. Then we have the pseudo section that was modeled. So this and this should look very, very similar if our model is good. And we can see that they do look very similar, and the residual is very, very low for this data set. So that suggests that the model that we've created should be relatively reliable within certain constraints. And that would give us some trust in the result that we have come up with here. If the residual is still quite high, if that residual was sort of 10–15%, then we would probably want to go back and start looking at, can we apply some other inversion processes to try and improve the fit of the model? Do we need to take other data points out? And one way that we can do that is we can actually look at how each of the data points in the modeled pseudo section compares to each of the data points in the real world pseudo section. So if I was to say edit data again, and I look at the statistics, this plot on the right hand side shows the measured raw values, apparent resistivity values, against the modeled apparent resistivity values. So if the model fits perfectly, then these two values are going to be the same, and so the data points will all sit on this diagonal line. And we can see here we had such a low residual that yes, most of the data points do. If you start having data points that are sitting out here, then that is where the model has really struggled to fit the data. And so what we could do is we could actually filter those data points out by setting a threshold with this green line. And as I wind it to the left-hand side, we can see that it will take some of those outliers out, and it will tell us how many data points we're removing. So this can be useful, again, to try and improve the fit, but you have to use it with caution. If you take out too much data, you will always end up with a better fit because you are taking out the problem. You're kind of, in a way, ignoring the fact that you have this problematic data. So it should be used with caution, but sometimes it can be helpful just to allow the model to work better on those data points that you are more confident in. And then you just have to accept the fact that it has reduced scope in some areas where you have removed those data points. Okay, right, that was a very, very rapid run through of all of that in what is an incredibly hot UK. I mean, I'm not used to it. So I would just remind you about the workshops that we're doing at GSA. If you'd like to learn more, do this in more depth at a slightly more manageable pace, then do Google GSA 2020 and have a look at the lineup. And so with that, I will stop sharing my screen and I'll ask Frederick to join me and let me know if there are any outstanding questions that we need.